Today's topic is decommissioning and its role in the energy transition, obviously strongly linked to the decommissioning module that is part of the larger oil and gas module on our platform, TechnologyCatalogue.com. I'm not sure if you have all seen that module, but perhaps just before I hand over to the speakers, I can show you where to find it on the platform. So if you go to the homepage, TechnologyCatalogue.com, and you navigate to the oil and gas module, you find a dedicated module there to decommissioning. It has an overview of technologies obviously related to decommissioning in the broader sense. So you see different types of technologies in the range of access technologies, one that you see here, intermediate energy solutions during decommissioning, for example, offshore platforms, as well as subsurface decommissioning technologies. At the top of this module, you also see several expert companies that can provide dedicated expertise. So it is actually related to this module that I'm glad to introduce our speakers of today. So today we have three speakers, all from the Oil and Gas Innovation Center from Curtin University in Australia. So the presenters today will be Klaus Otto, Stuart Higgins, and Christopher Murphy. And Klaus, may I hand over to you to introduce yourself and the team further and kick off with the presentations, and then I'll come back for the Q&A.
Okay. Thank you, Vincent. I hope you can all hear me well. Good morning and good afternoon, everyone. We're very happy to be part of this webinar organized by the Technology Catalogue. We have three presenters today, and I would like to introduce my colleague, Stuart Higgins. He is the Deputy Director of the Center at Curtin University and also the Program Lead for Decommissioning. And then we have Christopher Murphy. Christopher is a well engineer with decades of oil and gas operational experience, and he will talk later today. As an introduction to the Center for Oil and Gas Innovation at Curtin University here in Perth, our focus is on decommissioning, and you will hear more about that today. But it's also we're looking into and working on the energy transition as we go towards the net zero pathway. We also work on the hydrogen and CCS. But today we will focus on decommissioning, and I will start off with the first dot point, decommissioning in the energy transition. And then Stuart will talk about strategies, challenges, and opportunities. And then Stuart and Chris will conclude with the last topic on relevant decommissioning technology needs. So if I can have the next slide, please. Next one, please. Okay, there we are. So I don't know what your view is, the audience online, but I see decommissioning playing a very important role as the industry is transitioning over next decades towards net zero. So while the world is still and will be dependent on fossil fuels for the decades to come, the demand for fossil fuel and especially gas will not wane quickly. After maximizing the recovery of our oil and gas fields, cessation of production will accelerate in the decades to come, and that will then necessitate also the decommissioning. We will focus today more or less on Australia, but we are of course aware what's happening or in the North Sea and in the Gulf of Mexico, for example. So in Australia, the decommissioning is a huge liability to the nation, so that's to the companies, but also the taxpayers. But already recently, the industry is starting to get serious about about decommissioning, and that's also because the regulator and the public is demanding it. So as the industry, and that's not Australia itself, I mean the Commonwealth, as you can hear from the news, is promising to reach net zero by 2050. I think decommissioning has to play a part on that journey. So we see decommissioning also in the context of circular economy. So the benefits and the drivers for integrating decommissioning in circular economy is, in my view, reduce decommissioning costs and increase the life cycle value of offshore infrastructure. That would include, for example, the reuse of facilities, pipelines, and wells. Also, the recycling or upcycling of waste like plastics from flow lines and so on. And for Australia, this may establish a new industry, a decommissioning industry. We're not there yet. It may provide regional economic developments and jobs. I also want to point out here, there are two national initiatives in Australia, which have been seeded and instigated by the National Energy Resources Australia. It's a Commonwealth Growth Centre. The first one is called CODA. CODA stands for the Centre of Decommissioning Australia. That is a cluster or an initiative with operators and service companies related to decommissioning on a national level. And attached to that is NDRI. NDRI is the National Decommissioning Research Initiative. So that's where the research and technology developments are funded. Both CODA and NDRI enjoy funding from industry. If I can have the next slide, please. I thought we should at least show you Australia in one slide. So here is Australia. You see we have three main oil and gas producing provinces, basins, the Carnarvon Basin to the west of Australia, and then northwest we have the Browse, and then in the southeast we have the Bass Strait, one of our older gas fields and oil fields. So we have about 1,000 offshore wells, 59 platforms, including FPSO, and the liability for decommissioning of these assets over the next decades will range up to $40 billion US. So there's a substantial amount of money and a liability, and most of that deals with the wells, plug and abandonment, and the pipelines. Now, our pipelines in Australia, they're not short. We are talking about really hundreds of kilometers or thousands of kilometers of pipelines which need to be decommissioned over time. At the moment, decommissioning is quite new in Australia, so we haven't really decommissioned or removed the platforms yet. Some of the FPSOs have sailed away, but we're now at the beginning of a decade at least, and you can see that in the graph to the right. We need to invest, or the industry needs to invest half of that 40 billion US in the next decade on decommissioning, and wells will be a major part of that. So with that, I would like to hand over to Stuart, and he will start on the next part of our presentations.
Thank you, Klaus. I'll just spend some time on this slide, just verbally articulating these bullet points and the background behind them, because I'm not sure of the audience and their knowledge about the context of what's happening and what has happened in Australia that's setting up the current decommissioning drivers. So the first bullet point there deals with trailing liabilities, which is a principle certainly in the UK North Sea sector. But I'll just give a bit of a background first in terms of decommissioning in general and how that's regulated. So if we just talk about in federal waters, so we're not talking about state, we're talking about 3 nautical miles from the coast, Decommissioning is managed by NOPSEMA, which is the National Offshore Petroleum Safety and Environmental Management Authority. And they have accountability for all safety and environmental related matters in Commonwealth waters. And there's a particular act called the Offshore Petroleum and Greenhouse Gas Storage Act, and the regulations, which controls what NOPSEMA, what its accountability is, and it also drives what is allowed and has to be undertaken in terms of decommissioning. So the base case in the Australian context under the Act and the regulations is total removal, but there are some federal government guidance that gives some flexibility to leave infrastructure in place. And there's words around equal or better environmental outcome compared with total removal that you must demonstrate to the regulatory authority. And it's around this acceptable level of environmental impact, which is the very difficult thing to prove. And on top of that, we also have a Sea Dumping Act. So there are two levels of legislation which have to be satisfied in order to leave infrastructure in place. Now, this whole topic there's been a lot of activity recently around this, and it started back in 2018, where the federal government issued a discussion paper, and you can access it online. And it was looking at exactly the plot that Klaus was showing earlier about whether the current framework was really fit for purpose and whether it was going to be able to cope with the increased levels of activity. So they started this review process, and it was fundamentally identified a number of issues around decommissioning obligations, the legal responsibility and the financial responsibility. And while this was out for public discussion, there's a couple of incidents that occurred which precipitated probably far more urgent action than what was previously thought would occur. So there was it's called the NOGA incident. NOGA stands for Northern Oil and Gas Australia, and they had an aging FPSO which was sold to them by a primary operator, and they were probably a third-rate operator, publicly listed company. And as a result of that, they had insufficient capital to really run the facility. They ran into some safety issues. The regulator shut them down. They went broke, and now Australia was left with this rather large FPSO, a bunch of wells, and no one to pay for the decommissioning. So as a result of that, this is now cascaded into a whole series of actions from both the federal government and the regulator NOPSEMA, which is now driving what the operators must do and forcing a timeline. So now the government has introduced trailing liability legislation. It's just been passed recently. And on top of that, NOPSEMA has now flexed its regulatory muscle and is now dictating to operators with official notices that they must act in certain timescales. And so now operators are being forced, and it's not unique. It's across all the basins and across all the major operators are now being forced to show action and to start decommissioning. And the timescales range between sort of mid-2020s to 2027, and this is across all the basins. There are some recent changes that are now driving decommissioning to occur at probably a far greater rate than what was expected, and also a number of the operators who thought they were going to pull out of the country and pass on their liability to another third-tier operator is now not happening because the trailing liability is actually retrospective. So that's a change, and it's both a challenge and an opportunity from a decommissioning perspective. In terms of reuse and repurpose, as Klaus indicated, it's not really mature in the Australian context. Probably the only example where it's being discussed at the moment publicly is in reusing offshore and onshore infrastructure for CO2 geosequestration. So there is discussion around the Bayu-Undan field considering that, and it's also been actively discussed by Santos in the Cooper Basin in Central Australia in terms of all the depleted reservoirs and using that as a central CO2 hub. In terms of leave in situ and reefing, as another example, again, it has very limited use up to this point. The leave in situ and reefing is controlled by NOPSEMA in terms of the environmental plan that has to be approved, but then the Sea Damping Act comes into play as well. And so apart from a limited number of wellheads left on the seabed, an FPSO rigid mooring system being left on the seabed, some mid-depth riser buoys being moved to another location and used as an artificial reef, not much has occurred in the leave in situ and reefing potential decisions and solutions for decommissioning. In addition, in terms of the supply chain maturity, because the activity levels have been so low and they are spasmodic, there is not really a in-place supply chain dealing with decommissioning in the Australian context, not like other regions in the world where it's far more advanced, the Gulf of Mexico and the UK. And the final change in driver and context is to do with the waste disposal pathways. The current very hot topic at the moment from a regulatory perspective and from an operator perspective is the disposal of plastics, especially offshore. And there's been some recent legislation changes, and essentially to encourage the development of a circular economy, the Recycling Waste Reduction Act was introduced in 2020 federally. And essentially is what it's saying, it's a progressive thing, but by July 2022, you can only export waste plastics that have been sorted into single resin polymer types and further processed, or you're including them as a processed engineered fuel. So the usual pathways of, for example, flexible flow lines, being able to roll them up on a reel and send them internationally into Southeast Asia for disposal is no longer available to operators. So this is a key and major recent change that has occurred. On top of that, from a naturally occurring radioactive material disposal pathway perspective, there's very limited capacity in onshore Australia to actually dispose of that radioactive waste. Australia does not have a national, at the moment, does not have a national disposal facility. It is being mooted in South Australia, but has not yet been actually approved. So anecdotally, we believe there's a whole lot of norm that is just sitting in local temporary stored locations. So that sets out the context and some of the challenges. If we just move to the next slide, and I'll just introduce that. So we're now going to discuss a range of what we think are relevant decommissioning technologies, and these are primarily the focus of the Curtin University Oil and Gas Innovation Centre, and they focus around key questions and uncertainties really impacting the decommissioning cost. And that's primarily around wells and saving well cost. This is well plug and abandonment cost, and issues around pipelines, because they were 30 to 40% of the cost estimate as well. And the key decision and uncertainty there is whether you can or cannot leave them in place. So we will touch on well P&A first, which is the first topic here, and I'll hand over to Chris shortly. Then we'll deal with marine environmental assessment and potential contaminants, and this is about leaving pipelines in place, and then we'll talk about onshore waste disposal. So I'll hand it over to you, Chris.
Thanks very much, Stuart. So wells, you'll notice from the slide showing the Australian map that wells, it represents 40 to 50% of the cost of the decommissioning offshore for Australia. And if that offshore decommissioning is $40 billion US, wells could be in the $16 billion range, which is very, very significant. And Stuart and I actually put a paper together and was published by APIA, and we presented at the conference earlier this year. And our estimate from analyzing the wells is that if we were to apply capital restoration and minimize operations with rigs, i.e. go rigless wherever possible, there is a potential 40% or more cost reduction possibility, which is extremely significant. Now, CODA have issued a directive, a wish to reduce our current estimate by 35%. The UK did the same thing in 2017. and they've recently adjusted that. Earlier this year, the OG Oil and Gas Authority issued a strategy paper indicating that they were looking for greater than 60% cost reduction in well decommissioning costs. So it's a very, very large numbers. Now, the two things that we have to consider in Australia and everywhere else that is particularly governed by legislation and particularly safety case, which is the UK, there are two things, and it's annular barrier verification, and we'll explain that on the next slide, and barrier element integrity for deep set control lines. And what does that actually mean? Well, in a well that is in a reservoir, over the last 10 to 15 years, we've installed multiple pressure and temperature sensors and injection capability into those wells for de-waxing, etc., etc. And that's a very important part. So if we can go to the next slide, I'll show you some diagrams because it makes a lot more sense when you see what a well actually looks like. So on this left side, you can see there is a well where we're going to try and execute this program. There is in the center, there is what we call a tubing string, which goes all the way from the surface down to the reservoir. The reservoir in this particular case is shown as a light gray rock on the left-hand side. We normally have a casing string, which is usually metal, placed in the ground and cemented in place, and then we perforate through that with explosive charges to access the hydrocarbon. When the hydrocarbon is depleted to a level where it becomes sub-economic, we go back and we say, right, we'd now like to decommission this well, and the regulations that we use in Australia are they're the same as the UK and or Norway, which is basically based on caprock restoration. What is the caprock? Caprock is quite simple. It is the geological formation that overlies the oil and gas reservoirs, which if it wasn't there, there would be no hydrocarbon in place. It would have leaked over the millions of years. So we want to re-establish that. And the areas that are important are the areas that we've installed in the caprock, which is the multiple casing strings, which you can see on the diagram. Obviously the internal tubing string, and we want to place barrier material in that well that allows us to determine that well will be isolated forever. So on the right hand side, you can see pictorially there is an oil zone at the bottom. There's a gas zone. Gas obviously being lighter than oil, sits on the top part of the reservoir in a lot of reservoirs. Some reservoirs there's no oil, but overlying everything is a caprock, and it's our intention that the regulations as well, not just ours, that we restore that caprock, and how we can do that very cost effectively is using rigless riserless technology. So if we can intersect into that, working inside that well without accessing a large rig operation, an estimate of a well in the UK from a platform, Southern North Sea, roughly $5 to $7 million US for an intervention. If we can reduce that by 40 or more %, it's extremely significant. And our current costs are slightly higher than that. So there is a huge, huge benefit for applying rigless riserless technologies and caprock restoration. And the technology that we're really looking for is the annular barrier verification, because it's extremely difficult to determine that outside the tubing strings we've placed in the ground, there is a barrier element that will last forever. Basically, the regulations say you are looking at geological time. So that's in a nutshell what we're looking at. It's a very large piece of work going forward for Australia. As Klaus mentioned, there are approximately 1,000 wells offshore. There are multiple thousands onshore, but we focused our paper on just looking at the offshore environment. And if we can apply that, we can save not just the operators, it's the taxpayer. There is a very significant burden in all countries where there is a decommissioning program ongoing, that the taxpayer does in fact pay a large percentage of the decommissioning cost. So that's all I wanted to say. It's very short, very sweet, but of course, wells is such a massive component. So I'm happy if you've at least got something out of it, understanding what a well looks like and what we're trying to do. That's fantastic. So next slide, please, if you would, Jeremiah. Super. So I'll pass back now to Stuart. If there are questions at the end, please feel free to ask. we'll be here obviously throughout the whole of the 1 hour allocated thereabouts.
Okay, so Chris's slides were focused on the wells. This slide is, and the one after it, which we'll move to shortly, is focused on pipelines, so the other key cost component. So as with jacket structures, but also with pipelines, there have been multiple studies investigating the benefits of subsea structures on the habitat value of marine organisms. And this is around the justification for sea dumping, that you're not just dumping waste on the seabed in a justification to leave pipelines in place, that you're associating some sort of marine ecological value to them, and effectively it's an artificial reef. So you're justifying the criteria and the principles within the Sea Dumping Act and the IMO London Convention and London Protocols. So there's been lots of work around the ecological value, but there's not much work in terms of the negative side of the argument, potentially, which is the contaminants that you are potentially exposing that improved ecological value to. And so this is around toxicity and bioaccumulation, and actually, ironically, the potential to reduce the biodiversity of what you're actually arguing in the first place that's of benefit. Other issues that are also of concern are biosecurity concerns if the structures are moved to new locations for reefing. So the primary concern for both the regulator and operator is the lack of science-based evidence for the impact of oil and gas infrastructure on the marine environment, not only for removal, but for leaving place as well. And as I said, this is fundamental in the acceptance of the environmental plans and the sea dumping permit applications. And it can be quite difficult to actually demonstrate this acceptable level of environmental risk. And I'll get to the project in a moment, but we are focusing primarily at the moment on mercury and naturally occurring radioactive material, and that's because of its propensity to impact the marine environment and do so for a very long period of time. That is the primary focus. Can we just skip to the next slide, and I'll just explain in terms of that project. We just talk about norm and mercury. So no, go back one. That's too many. Let's go back one, please. Okay, so we were talking about before in terms of the national research initiative, and this all comes under the umbrella, and I'll just explain this for a moment, under the umbrella of the National Decommissioning Research Initiative. This is NDRI, and the project that we are working on, which is what's titled there, the risk-based marine impact assessment of mercury and norm, and this is primarily around leaving pipelines in place. This is just one of 7 topics that NDRI are focused on. The first program, just to give you a bit of an overview, the first program is looking at, as I said before, around assessing the habitat value of the infrastructure for fish and marine life, the connectivity of that marine ecosystem, and also understanding the spread of risk for invasive marine species. That's one side of the research focus under NDRI at the moment. These are 2-year programs. They kicked off a bit over 12 months ago, so majority of the projects are halfway through. And the second program is actually more focused around the degradation of metals in the marine environment and the degradation of plastics in the marine environment. That's the second topic. And the third one is the title that I'm showing you here. So just to give a quick overview of what we're doing. So primarily we're focused on norm and mercury. So if we just put the first slide up, it's a busy picture, but it'll give you an indication of the sorts of complexities that we're having to deal with. So could you go to the next slide? Yeah. So on the left-hand side of the figure is representing a piece of pipe being left on the seabed, and there are sort of 2 main scenarios that we're considering. It's obviously closed until the degradation of the wall thickness is such that you get seawater ingress, and then it's open to the environment. So we're primarily concerned with radium sulfate contaminated scales and barium sulfate scales. And there are both an external radiation component through the pipe wall, and then once the pipe is breached, we then end up with a dispersion and an exposure into the environment. So I won't go into all the into the figure in detail, but there is a very complex relationship then of how that, it can either be radium and it can also be polonium, how that radioactive contaminant enters both the environment, how it partitions into the sea, how it partitions into the sediment, and how bioavailable it is to all the organisms sitting both in the sediment and in the water column. And so we are studying this in detail and then coming up with a risk framework. At the moment, in terms of the marine context, this work is hard. There's hardly anything published on this. And so it becomes very difficult to assess the risk. And so we're trying to put this all together and looking at the effects of bioaccumulation and toxicity on the marine environment so that we can actually come up with a determination and a methodology for coming up with what is an acceptable level and being able to back calculate that into a contamination level that's sitting in the pipeline. In the case of naturally occurring radioactive material, the timescales, because of the half-lives of radium and the ingrowth that you get, which actually increases the activity level of the radiation at a function of time, we're talking about in excess of 1,000 years, where this continues to be a potential threat. So we're having to forecast out as well as deal with all the uncertainties. If you just go to the next slide, the other thing that we're looking, the other primary contaminant that we're looking at, if you go to the next slide, please, is mercury. Mercury doesn't have the radioactive half-life, but mercury stays around for a very long time, and mercury can exhibit itself in the pipeline in various forms, but apart from elemental, but we also end up with hydrogen sulfide as well in corrosion scale. By the same token, its pathway into the environment is complex, and its pathway into the sediment and partitioning into the water column is also complex. And mercury in and of itself, and mercury sulfide, is not particularly bioavailable, but the tricky thing is when it forms in its ionic form or actually methylates is the key determinant in terms of impact from a toxicity and a bioaccumulation point of view. So in the same way that we're looking at norm, we're also investigating mercury, its contamination, and trying to determine what's the acceptable level, and then back calculating that to the sort of contamination levels that are in pipelines today. If you could just go back a couple of slides to the main presentation again, where I just had the dot points. So back 2 slides. Yep. So that's dealing really with the first dot point under marine environmental assessment and potential contaminants. From an operator's perspective, they will say that you should be able to manage this by actually dealing with the in situ contaminant and treating it in situ, so that you are reducing the contamination levels to an acceptable level, and therefore you can substantiate leaving the infrastructure in place. We think there's still a lot of work in terms of this contaminant treatment, and to our knowledge, this in the Australian context anyway, this has not been fully implemented, nor has it been accepted by the regulator yet. So in terms of contaminant treatment, both from a mercury and a norm perspective, it's still to be proven. The other key issue that needs to be addressed, and is a major uncertainty, and it's linked to both of the 2 dot points above, is the in situ measurement of contaminants. At the moment, there is no field-ready piece of instrumentation that you can deploy to measure accurately the species of the contaminant or the levels of the contaminant, and this is across both norm and mercury. So in terms of the initial risk assessment, and also the verification after a contaminant treatment, there is nothing in place today that is field proven that I think that the regulator would accept. It's still needing verification. So that is a key piece of technology that is required in terms of the contamination. In terms of local onshore processing of waste materials, this reflects back to the point I made earlier. Because of the volumes and because of the lack of maturity and the current changing regulations, there is limited capacity at the moment for local onshore processing of waste materials, and certainly given the changes to plastic regulations, there's a driver now for international technology providers to actually come and offer their services once they've deduced the sort of the inventories that are expected as a function of time. I'm sure there'll be various business cases developed to actually deal with that problem. I think that's all I've got to say. So thank you for your attention.
Klaus, any other closing words from your end? Otherwise, I'll take over for the Q&A.
Yeah, well, why don't we start with the Q&A? So I think limited time.
All right. So thanks a lot for the presentation. At this moment, I would like to open the floor for questions. Just from a process perspective, I see some of you already found the Q&A on the side. So if you can please type your questions using the Q&A option, would be great. If perhaps you can also mention your company name and location to put things in perspective, also for the speakers, and then I'll pick out a couple of the questions and just see how much time we have, and depending on how many questions will come in. For the presenters, I will leave it up to you to decide who wants to answer or who feels best placed to answer. So let's start with the first question from Yuri Sokolov. Basically asking, what's the main driver for the commissioning plans? Is it the typical reservoir depletion, end of field life, or perhaps more pressure in terms of, I guess, the energy transition topic on reliance on other energy sources?
Can you take that, Klaus?
Go for it.
Yeah. Principally, it's reservoir depletion, which means that the assets are going sub-economic. That's by far the most prevalent reason. Now, there is also a comment there about structural life expiry. A lot of these platforms have been in tens of years, but it's possible through analysis to evaluate whether those platforms and indeed pipelines and wells could be used for something else, and that is being looked at, not just in Australia, principally for CO2 sequestration. So the number one reason is economics, right? Depletion. But it's a big issue all over the world. The vast majority of places I've been involved with, which is international for many, many years, it is pure economics, reservoir depletion.
Yeah, I'll just add that, and I didn't mention it before, but given that from the regulator's perspective, NOPSEMA, because they have been placed in a position because of circumstance where the decommissioning plan has had to change because of integrity issues. They've now introduced a strategy and a plan such that they are dictating timelines. So, for example, that anything that's floating a buoyed structure, which this is based on experience, once it's ceased its use, then within 12 months it has to be removed. They're also, in terms of wells, if they've ceased production, they're now forcing them to be P&A'd within 3 years. This is their wish, and they want to have that in place by 2025. And in terms of structures and other equipment, they want it removed within 5 years of ceasing production. So they are reducing the window, and they're reacting because of what they perceive as inappropriate behaviour from the operators, and then they're left with infrastructure that's integrity is so poor that you cannot actually do anything with it. So that's the counter. And I mentioned before that really in terms of, there's another question there about reuse of offshore structures, wind power hubs, hydrogen, etc. It hasn't really gained any credible discussion around that, other than the only reuse purpose that had any credible discussion is around CO2 reinjection.
thanks for that. And perhaps that does link to another question that came in from Paulus, and says, how does the real decommissioning thinking in Australia compare to what's happening elsewhere in the world? Because I mean, we're based here in the Netherlands, close to the North Sea. We actually see a lot of activity where offshore structures are being used for part of wind farm and transformer bases, etc. And how do you see it in Australia? Are we in a different view there?
I think the issue is if you looked at the map that Klaus originally showed, the areas, the two main basins in the northwest, the Carnarvon Basin and the Browse Basin, they are so remote. They are in the middle of nowhere. There is no population on shore. So it's unlike Europe, where you have ready access to market, and so I just don't think it's economically viable. Potentially in Bass Strait, yes, where it's a very high population area, and they are proposing a large wind farm down there. But the energy transition plays for the northwest of Australia around solar and wind over thousands of acres, connecting a subsea power cable connecting the whole of Southeast Asia. I mean, it's on a huge scale, and converting the limited number of facilities we've got to wind generation just wouldn't make economic sense.
All right, thanks. Hey, just picking up another question from Pat Brandon here. Why does Australia need to have foreign companies enter the market when it has technology solutions of its own, particularly for the recycling? I think that was the question, was meant to focus on the recycling element.
I was on the federal government website, and you can go to this yourselves and look up the latest policy for the plastics recycling. The federal government has listed, I counted them, there's about 80 odd companies there that are designated recyclers, but when you actually go to them, they're landfill. There must be a very limited number that would be able to fulfill the requirements of the new legislation. That doesn't mean it won't happen, but I think at the moment the legislation is leading and the market's lagging.
I also think for what we talked about, the flow lines, umbilicals, cables and so on, there's not an established industry yet to recycle or upcycle. And that will come if the market is right. Yes, there are technology developments going on, but at the moment, I think the industry is still struggling where to go at the moment. Industry, and as you were saying, Stuart, distance is a major hurdle. So these solutions need to be close to shore and onshore, and we need to build these facilities eventually. So that needs to come.
And actually, great to see, linked to that, I see also a question coming in, or maybe more a comment from Sasha from Oleology, who is already reaching out to you, that they have a technology looking at mercury removal. So if you're not yet connected, maybe good to do so after this webinar to explore further. Thanks for sharing that, Sasha.
Very good.
There was another question coming in. I'm not sure who asked the question, but it was around it's still the topic of mercury removal. I think Stuart, you mentioned that the shipment of flexible flow lines to other locations is no longer deemed acceptable by the regulator. There was I think a practical question also around the mercury disposal. Are you expecting that the mercury has to be removed within Australia, or that if it's regarding topsides, that the topsides will be shipped somewhere else for further decommissioning and waste?
Yeah, if you go to the federal government website that and I can provide the link, that are talking about the new waste disposal. I mean, Australia is still party to the Basel and Stockholm Conventions, so in terms of the transportation of waste. Now, I haven't read that in detail to know, but but I suspect mercury would not be allowed to be transported internationally without some sort of permit.
Hey, Vincent, there was an interesting question about coal mine abandonment and restoration. If I can comment on that, it's a bit off topic, but Australia, the coal mine and mining industry do have very strict regulations in terms of restoration of landscapes and a rehab of mines. So that's way more advanced than we have in the oil and gas industry. So it's very regulated, and it's basically you will restore your mine site as you found it before you started digging. So that's basically it. Very much aligned what the regulator is saying to the oil and gas industry. You will remove everything. So I'm pretty sure there are exemptions, but it's a good question. The coal mining industry is very advanced and regulated in terms of abandonment and decommissioning. I don't know about the plastic part though.
All right, and thanks for picking that up. And perhaps also linking on the broader topic, and again, I guess something that's also being looked at other parts of the world. There's a question that's just come in from Bettina, who's asking if you could comment on the suitability of the existing pipelines for hydrogen transportation, or is that wishful thinking? Is the part of the question.
I think there's an SPE discussion topic on that in the next week or so. Yeah, I'm sure, and I've noticed the various engineering consultancies are rolling out presentations on this. So I don't know whether a full survey has been conducted to look at material types and whether they would comply with a hydrogen specification. And the welds, of course. But yeah, I can't imagine it's a slam dunk. I imagine that there are many technical uncertainties and risks that would need to be assessed.
Comment, the domestic gas pipeline from the north down to Perth, they are considering blending the natural gas with 10% of hydrogen. And I think that's where the limit is, based on the material of the pipeline, to avoid any hydrogen embrittlement. So it's a bit like what's happening in Europe as well. They're looking into that. So I think to have a pipeline for just hydrogen is going to be extremely expensive, considering the steel you need to consider.
And then a clarifying question by Alan, who's asking if you could perhaps just elaborate what you exactly mean with rigless or riserless wells, and further explain the cost saving that we can achieve using CRR. Yeah,
sure. So capillary restoration is a basic fundamental principle behind the UK well decommissioning guidelines and the current NORSOC D10, which is the Norwegian version, both of which are acceptable in Australia by NOPSEMA, right? Now, so let's make the assumption we will restore the caprock. The question is, can you do it riglessly, right? And by riglessly, we mean, do you need to bring in a rig, a drilling rig, or an equivalent rig that can pull tubulars out of the ground? Or can you do it with something that's less expensive but can satisfy the regulatory requirements for a barrier that will be a set of barriers which will be in place forever, right? So rigless means if you have a subsea well in the UK, there've been quite a few cases, and certainly in the Gulf of Mexico, a lot of cases where we've actually abandoned wells in the subsea environment using monohull vessels, which is a standard vessel like a ship, right? Not a drill ship, and we've intersected into those wells using wireline and the capability to flow fluids. And fluids in the case of barrier material is we mix cement, it's a fluid, we pump it into place and it sets. So rigless means you're trying to reduce the cost by using alternative technologies that do not include drilling rigs, right? That's basically the fundamental concept behind rigless and riserless. Riserless is only applicable to subsea environments. If you don't have to put a riser so let's say you're in 1,000 meters of water and you have a wellhead, how do you get fluid into that well? If there is an existing tree, you can run down lines, flexible floor lines, or some other equivalent, so you can circulate into that well and create a circulatory path to place your barrier materials without the use of a riser. A riser ordinarily means you have to connect from the well, from the top of the tree back to a vessel. Quite often it's a drilling rig, or it's a relatively expensive monohull purpose-built intervention vessel. So that's what we're talking about. We're trying to reduce the cost whilst maintaining the integrity of the well forever in the decommissioning phase. And the UK is definitely moving down this road. But for the vast majority, if you're interested in decommissioning in a rigless manner, look at the BSE website, and you'll find that since 1980, the vast majority of wells have been abandoned in the Gulf of Mexico, which is several thousands and thousands of wells, were in fact decommissioned using rigless techniques from shallow water platforms. It's much more prevalent in a platform environment, because it's easier to access the wellhead because it's in the air, it's not under the water. So I hope that answers the question.
Yeah, thanks for that clarification, Chris. Then perhaps another quite practical question from Gavin Booth from the Pipe Tech operations in Aberdeen. And he's asking, how are subsea pipelines in Australia currently hydrocarbon free prior to decommissioning?
I haven't done it personally, but it's water flush as far as I know.
Right, I hope that
there was another question there around couldn't we somehow bind the mercury and the norm to the pipeline wall so that it would remain in place and not distribute to the environment. The trouble is with both norm and mercury, they hang around for a long time. So, and this is another area of uncertainty that we're not working on, but others are working on. But given a pipeline and its burial and the coating systems, you know, what are the modes that it breaks down and over what time periods? And we think, yeah, within 1,000 years, which is certainly within the timescales of norm and mercury, that they will eventually end up in the seabed. The pipe wall will disappear, so maybe you can modify the bioavailability of those contaminants and bind them up. But we're looking at the very complex geochemical reactions that occur in the seabed that can actually break down something that normally is not soluble in seawater. So it's a very complex. This is where the complexities are. It's in the chemistry, the geochemistry, to actually come up with an argument that something that is normally insoluble can actually become soluble and then bioavailable. It's one of the main uncertainty areas in this contamination problem.
Thanks. I think we have time for one more question before we'll bring it to a close. And I'll pick this one from Colin Black from the UK, who is asking, have you also researched pipeline concrete mattresses removal, which are held together with polypropylene, causing microplastics?
No. There is a group here in the Corrosion Centre, I didn't mention before, but they've been given the NDRI project on degradation of plastic. So they've looked at, and this is degradation of plastic or polymers in the marine environment. So over the last 12 months, they've put a large model together to look at all the degradation mechanisms possible, from microbial to UV to abrasion, all as a function of depth over the basins of interest in terms of the chemistry of the water. So they're modelling what those degradation scenarios are and mechanisms are to work out what is the rate of release of plastics to the environment. If that is validated, then the next issue will then be looking at the environmental impact of that. I've heard various opinions on that as to whether it is a real issue, or the opinion I have that compared with mercury and norm, it's not an issue. But that's not before the regulator with a solid argument yet.
Okay, so I think with answering that question, I would like to once again thank you three for presenting and answering all the questions today. Good to see that so many questions have come in. Also good to see, I think that that you really, of course, today presented your Australian perspective, and lots is happening around the globe, whether it's in other hotspots like the Gulf of Mexico or the North Sea, of course. And I think also from the questions, but also from what we see from our end as a platform, engaging with other operators, I think there's certainly opportunity for cross-learning. So I know, for example, the mercury topic, it didn't really come up here in the Q&A, but some operators here around the North Sea have also found technology to essentially remove the mercury, which allows them to dispose the steel as a waste value stream. So I think, yeah, for Australia, it would be good to tap into that knowledge as well.
So we are working with the University of Aberdeen, so we're aware of some of the things, especially in Thailand as well.
So for all the attendees today, thanks for joining. You will also receive a summary email after the webinar. So if you have any further questions or want to reach out to Klaus, Stuart, or Christopher, you can do that via us. Either reply to the email or simply contact us at info@technologycatalogue.com, and we'll make sure that the questions will be forwarded to the speakers. Thanks again, and hope to see you all again for the next webinar. Bye for now.
Thank you, Jeremiah.
Thanks, everybody.